lovely introduction, and also thanks to Elia for his wonderful talk that we had before. So there were already a couple of spoilers for my talk in the quiz, but I think that is only a bit of a teaser for the actual talk. So today, like you said, I am a PhD candidate at Leiden Observatory, and I study these cosmic collisions, so these mergers between galaxies. And today I want to talk to you about what happens when galaxies collide and why are we interested in studying them. Why do they matter for the evolution of galaxies throughout the universe? So let's dive right in. And I want to start with some galaxies that you might be a little bit more familiar with. These beautiful images from the Hubble Space Telescope of spiral galaxies. So these are sort of, I guess, the most well-known types of galaxies because they're just so pretty to look at, right? What you see is this bluish glow of the collected starlight of millions of stars. So in these spiral galaxies, they are disks, which you see on the left side. If you see them on edge on, you see that they're very flat with this little bulb in the center. This works great. But then when you see them face on, like here, you see that they have these beautiful spiral arms. And inside these spiral arms, there are all these sites of young star formation. So these systems are like the factories of stars. They are very actively star forming with lots of young stars.
Point letters. No? Okay.
Yes, okay. And when we look at the anatomy of the spiral galaxy a little bit more, so I told you there's lots of young stars in the disk, in the spiral arms. There's this bulge where the stars are a bit older, and then all the way very deep inside here is the central supermassive black hole, which Elia has already talked about a bit. And now we call them supermassive black holes because they're much more massive than the black holes that we see closer to us, which form out of stars, basically. These are much more massive than that. But actually, on the scale of this whole galaxy, which is maybe about 100,000 light years across, that central black hole sitting somewhere here is actually very, very small. So most of the stars in this galaxy will know absolutely nothing about that black hole. But still, that black hole can be very important. And yes. Now there's another type of galaxies, which we already saw a bit about in the quiz, which are these elliptical galaxies. And they are maybe a little bit less well known because they're not as structured as the beautiful spiral galaxies that I just showed you a few pictures of. So they look more like these sort of ambient glow of starlight. And there's not so much structure to this. This one is a little bit dustier. But yeah, you see that they're a lot more like just ellipses with a bunch of stars. And we lovingly call these red and dead because they're not just different in the way they look, they're also different in their stars. The stars in these are, unlike in the spiral galaxies, very old, very evolved. And these systems, these galaxies, are not actively forming stars anymore. We call them quiescent. They are, in a way, dead because they're just not forming stars anymore. So we have these two populations of galaxies that are both quite common and they're really clearly distinct. And the first time that astronomers noticed this, that was already a big question, like why do we see these two very different types of galaxies? The star-forming spirals on the one hand, and on the other hand, the red and dead elliptical galaxies. So that's one of the questions. The next one, next thing that we noticed, I promised I will mostly stick to pretty pictures, but I like to show this because it's quite a fundamental thing that we've found in our observations. I'll walk you through it. So here we have the mass of the central black hole, so this comparatively tiny thing, basically. And then this axis is it traces the mass of the bulge of the galaxy, or basically the mass of the galaxy as a whole. And what we find quite consistently across many different sizes and types of galaxies is that basically as the galaxy as a whole is bigger, it also has a bigger central black hole. So what I've attempted to sketch here on the left is basically if we see a bigger galaxy with more mass, its central black hole is also bigger and more massive. And that may seem like something you would expect, but when you think about it, it's really not quite so much, because like I said before, the central black holes are much, much smaller than the galaxies as a whole. So like a star sitting somewhere here, maybe 20,000 light years away, there's no reason that it would know anything about this super tiny thing sitting right there 10,000 light years away, right? So that's not trivial at all, that these things, that the growth basically of the central black hole and the growth of the galaxy as a whole are connected, but somehow they are. So that is also a major question that we're actually still working on very actively in astronomy. The question, why are the growth of the galaxy as a whole connected? Why is that connected to the growth of the central black hole? And we think, or we know at this point, that interactions between galaxies play a major role in this. So we know that galaxies do not live alone. They often live in groups and clusters, and that means that sometimes they run into their neighbors. And when they run into their neighbors, they really disturb them quite a bit. So this is just one example of two spiral galaxies that get close to each other. And if you look closely, you see that there's this bridge starting to appear where some stars get pulled in by the gravity of the other galaxy. So they get pulled away basically out of their own galaxy. So in this way, these galaxy interactions disturb the galaxies. And sometimes that is a very violent process. If you have like a head-on collision between galaxies, they really reshape their galaxies very violently. So these are also two very famous examples. Like this one on the left, do you see anything left of the original spiral galaxies? No, it looks very, very disturbed and very dusty as well. And here it's the same thing. There is a lot happening here. This is a very violent process that really reshapes the galaxy. And I have a little video, which I hope I can get to work. Yeah. So here you see a simulation. You can choose whether you want to see top or bottom, because it's just face-on view and edge-on view. On the left, you see the gas, and on the right, the stars. So it's the stars and the stuff between the stars. And as the first encounter happens, you already see that they get these huge tidal tails, where tidal forces start to stretch out the galaxies. There's this bridge connecting the two. And as the second encounter starts to occur, you can really start to see the difference between the gas and the stars, because the gas is much more volatile. It is, blown out and pushed out much more easily, and it starts to get really disrupted. And a lot of this gas just completely leaves the system. It just flies off into space. Whereas on the right, after about 2 billion years, you can start to see the stars are really reassembling, and there is nothing really left of the original spiral. It starts to look more and more like the elliptical galaxies that I showed you before. So we think this is a very fundamental process where two spiral galaxies encounter each other, they collide, they merge, and over the course of about 2 billion years, they turn into this massive elliptical galaxy, which doesn't have so much gas left, as you can see here. And the gas that there is very warm. It doesn't easily collapse into stars anymore. So this is how mergers very much impact the evolution of the galaxies, because they strip away gas, they heat gas, they stop star formation, and they reassemble the shape of the galaxy to form these ellipticals. Yeah, but they don't do more than just reassemble the stars. They also cause new bursts of star formation. That is because this gas is pushed around a lot. It really bumps into other bits of gas. It gets compressed, and all that compression really triggers new bursts of star formation. So new stars are formed. And because this is a very fast process, basically, in all cosmic timescales, a lot of these stars are formed all over the galaxy all at once. So we get these bursts of star formation, which means that these galaxies can form stars at rates of tens or to hundreds times the rate you see in our Milky Way. And this is a very nice example of one of the earliest results from the James Webb Space Telescope. James Webb is very good at looking at dusty things. It has infrared cameras, looks at dusty things, young things, such as the youngest stars. So these things, these encircled blobs here are all very young star clusters. They're clusters of stars that are only a few million years old, really the youngest clusters we can find. And these are all things that we could not see before. With the Hubble Space Telescope, we really needed the infrared capabilities of the James Webb Space Telescope for that. So these collisions really cause these massive bursts of very rapid star formation. Yeah. And the other things they do is that this gas is also pushed into the cores of the galaxy a lot. So the cores, the centers of these original galaxies, they are very massive. They attract a lot of matter, basically. They have very strong gravity, basically, acting on the gas. And that means a lot gets pushed into those cores. It gets near the supermassive black holes, and it starts to fall onto it. It starts to accrete, and we get these quasars or quasar-like things that Elia talked about before. So this means that the black holes inside the galaxies can start to grow because of these. Because of these mergers, because of these collisions, the black holes go through this really rapid mode of growth. And it's no coincidence that the nearest quasar that we have, Markarian 231, so it's the quasar closest to us, is also the product of a merger. You can see the tidal tilts. It's in an advanced stage, but it's still clearly disrupted. So this is also a place where a merger has recently taken place. So I've told you that these mergers can trigger new bursts of star formation. They can also trigger the growth of the black hole. There's one other thing that they do, and that is something we call feedback in astronomy. So when these so many young stars are born, young massive stars, and sometimes the supermassive black hole starts to grow and starts to basically produce really intense radiation, that heats the gas around it, and it also blows out a lot of gas. So this is an image of Centaurus A, very famous radio galaxy, where you see these two lobes in radio, which is very highly ionized, energetic plasma, ionized gas that is being flung out of the galaxy by the central supermassive black hole, so by the quasar. And these processes can actually halt star formation because it heats the gas, and the gas can no longer form stars, and it just blows out a lot of the gas as well. But this process can also trigger new star formation. If some of this gas eventually falls back onto the galaxy, that will trigger new waves of star formation. And I want to emphasize here that this is a process we do not really fully understand yet as astronomers, so this is a very active area of research. And it's one reason really why we're interested in studying these mergers, because this is a major part basically of understanding how these galaxies and how these black holes grow up together, basically. And that brings me to ultraluminous infrared galaxies. So these are an ideal laboratory to study this growth of the galaxy and the black hole together, because all of these processes are happening in these things. So, and these ultraluminous infrared galaxies are all major mergers, so there are all these very extreme clashes between galaxies. We see them in various stages of the merging process. I would say this is the most famous ultraluminous infrared galaxy. This was the first one to be classified as such in the 80s. This is ARC-220. It was already part of the quiz. In my field, this is everyone's favorite object. I'm not kidding. Every time I've given a talk about this, everyone's been on for hours and hours about just this thing and all the stuff that they have learned about it in the past 40 years. So I want to use it as an example here. So this is the Hubble image of Arctic-20. You see it's in an advanced stage of a merger. You still see a bit of these tidal tills, but other than that, it's starting to look pretty elliptical. And it doesn't look super spectacular, to be honest. But when we looked at it in the infrared, in the 80s, when the infrared sky opened up, we noticed that it was actually extremely bright in the far infrared. In fact, so this is a near-infrared image where you see these two nuclei starting to pop up, these two cores. That's where the central supermassive black holes are. And notice it's two of them because it's the product of two galaxies. So there's two supermassive black holes here. They're very close together, but not quite merged yet. And this one in particular, one on the right, is extremely luminous. This thing on its own has the energy output of a quasar. So those things that Aaliyah was talking about, these super bright, super extreme things, when a central supermassive black hole is growing and creating matter, this thing on its own has similar energy output, basically. But it's all in the infrared, which means that it's all coming from dust, warm dust. So it's dust that is heated by either a quasar or by very young stars. And I mentioned that James Webb is very good at looking at dusty things. So here's a nice composite image with some starlight that you see from Hubble, and then all the red stuff here is warm dust that we see with James Webb. And when we looked at the center with our spectrographs, we also see these two very red points, or the nuclei, and then all these other things are basically places where there's a lot of star formation happening. So now you might ask, okay, so this thing, this center, has the energy output of a quasar, so it's probably a quasar, right? It has to be a central supermassive black hole that is growing. And that was actually one of the hypotheses that was already posited back in the 80s when it was discovered to be this weird thing. This is like the original R220 paper was already proposed that it was Seyfert-like, which is an 80s way of stating that it is like a quasar, or the starburst, so this burst of lots and lots of star formation. And the answer to this, like, is this a growing supermassive black hole? The answer to this is still, we don't know, weirdly enough. It's been 40 years, and I looked it up. There's 127, so after the paper that I showed before, there have been 126 papers published, refereed, that had Arctic-20 in the title. I'm not even counting things that didn't have it in the title. But we still don't know, and people have been trying hard. Very hard. But even with the almighty James Webb Space Telescope, we still have no idea, really. And the reason for that is twofold. One of the things is that this thing is extremely dusty. So this thing alone, where we think there could be a quasar, is basically like trying to look at a wall. In fact, this is an excerpt from an actual published very nice paper about it. It's interesting to note that the mass column density corresponds to a concrete wall 3 to 4 meters thick. So it is literally like pointing your telescope at a concrete wall. And that means that basically any direct observational evidence of this thing hosting a quasar is completely blocked from view. Even when we go to the infrared, it's blocked from view. So any smoking gun evidence of a quasar there, we just cannot see. The other reason is, because I did say this thing is super energetic, that is that we do know this thing is forming stars like crazy. So these are the two nuclei that I showed before, but now with very high resolution radio observations. So what you see here is the dust, basically. This is warm dust. And these things are about 300 light years across, which is relatively small. much smaller than the galaxy. And then below, all these red points here are sites where a star has exploded recently. So these are very massive stars that don't live very long, and to have, there's about 100 of these points here, plus the 2, and to have this many supernova remnants, so remnants of exploding stars all at once, means that you're forming stars at a crazy rate, much higher than anything we have in the Milky Way, or in other galaxies as well. And all of this is just happening inside this very small thing. This star formation is so extreme that we honestly do not really understand what this does, basically. We don't understand how much energy output this can generate just with star formation on its own. So that's the other reason why we're just not sure whether there's actually a quasar needed at all to explain this huge amount of energy that we're seeing. So it could still be a very deeply buried quasar, a growing supermassive black hole, but it's also possible that it's really just very extreme star formation happening. And with that, I'm just going to flash my own work very quickly. So basically, because we are very, all our conventional methods of finding a quasar here just fail because it's so dusty, which is why we need to look at more creative and more indirect ways to see if we can say something about it despite all of that dust. And one thing that I am working on in particular is studying the chemistry inside these things. So what that means is we look at observational signatures of different molecules. We can do them very well in the radio and in the infrared. This is a spectrum from the James Webb Space Telescope that we took, and some of these things that I've indicated are just the most, let's say, interesting molecules that we found here. There's actually a few more in there as well, but these are the strongest ones. And by piecing together which molecules we see, how much of these molecules we see, we try to make a picture of the chemistry that is happening in this system, in this gas, which might be able to tell us something about what the physical processes are, what the mechanisms are that are happening here. So it's a very, very indirect way of trying to figure out what the hell is going on inside that core. But the title here already says it. So far, it seems like this chemistry, even this very indirect way, is still, it's really pointing towards this being a very extreme burst of star formation rather than a quasar. So if there's a growing supermassive black hole in there, it's hiding really, really well, or it's just not really doing much at all. And that brings me to my conclusions. So just to summarize, collisions and mergers play a massive role. They play a really important role in the evolution of galaxies. They trigger new bursts of star formation. They cause the black holes to grow. But through feedback, they also regulate that growth by halting star formation. And for some systems, for basically what I call the messiest systems, we need to invent new tricks to add to the book to really be able to disentangle this star formation from the growth of the black hole. And the last thing I wanted to say is I had an absolute blast making all these pictures, just digging through the Hubble archives. So I hope you enjoyed them as much as I did. And thank you for your attention, and I'll be happy to take questions.
Yes, thank you for your talk. I was wondering, is this the only case where there's such a mystery around collision between galaxies?
It's a good question. So the question is this is RT20 the only case where there's such a mystery? And the answer is no. Oh, it's not going back. So the answer is no. There are actually other cases where we also don't know. There's also other objects, other galaxies which are even more obscure, which have even more dust in them. But this is, I would say, the best studied one. So this is the one where people, because it's nearby, it's the closest one we have. So we can study it in really high detail. So that's why people have looked at this, in basically every possible way. There are definitely others where there is also still a mystery, but people haven't looked into it as much yet.
So you're looking at messy dust, so that many heavy elements. Supernovas burst at the moment that there are no light elements anymore. Are they, with it blasting so fast because they're burning that fast with the leftover helium and hydrogen?
That's a very interesting question. So the question is are the supernovae going off so fast because it's depleting the helium, right? Because there's so much dust in there. I don't think so, I would say, because what you're mentioning is the supernova goes off when the star itself, the core of the star runs out of elements, right, to burn. And when that happens, I would say that doesn't necessarily have so much to do with the conditions in the gas itself at that point, because all these stars basically formed at once. So I think, and that star formation is also what produces the dust, basically. Does that answer your question a little bit?
It was a messy answer, but that's...
I think I would say the huge, it's more that the star formation rate produces like the huge amount of dust. It's more that than the other way around.
Okay.
Yeah.
Yes, so I also have a question then about, so you say there's a high rate of star formation because you see the massive stars go out really fast, or you see a lot of them. But could it also be that the mass function, so the formed mass, formed stars, the distribution is not equal to what we are expecting or we see in other places?
Yeah, thank you for an excellent question. So the question is, could it be that there's so many supernovae going off because the mass function is different from what we're used to? So the mass function tells us basically how many stars would we expect to see at a certain mass. And it is actually hypothesized a lot that in these merging systems, the mass function of stars is very different, actually. It's hypothesized a lot that it's what we call top-heavy, so there's a lot more very massive stars in these. That is something that is very hard to prove, because we can't really pick out individual stars to study in these systems. They're just too far away, and in this case, they're also too obscured by dust to really see them. So, but that is something that people actually consider a lot, and that is also, I think that adds to the reason why we see so many of these supernovae go off, because there are just a lot of very massive stars, and massive stars, they live fast, die young. They really are very bright. They do a lot, and then very quickly they just burn up and go supernova. They explode. So I think that is actually part of the reason, yeah. But that's something that's very hard to prove. Yeah.
Yeah, so from your own study, you showed this spectrum.
Yeah.
Is that then a point spectrum, or is that across from, let's say, a big picture amalgamation of inputs?
So the question is the spectrum a point spectrum, or is it from, you mean an animation from time, or from an extended source?
Yeah, more what is the focus, let's say?
Yeah, okay. So it's a snapshot, basically, so we can't really, we have just one observation, basically. We looked at the same ones, we took the spectrum once, so it doesn't tell us anything about time. The other thing is that because basically all these features that I've studied are in absorption, so they are the light from some background is hitting some gas, and that gas is blocking the light on very specific wavelengths. That's how we figure out in any spectrum basically what's in there. And because it's in absorption, we are actually looking at a very narrow line of sight towards, well, basically towards that very tiny, that very tiny core that we're looking at. So all this stuff that we're seeing is basically in a pretty compact region. Yeah.
Thank you.
So towards the beginning, you showed a video by Volker Springer of distribution of gas and stars.
Yes.
And my perception of how this should work is like the bullet cluster, where the gas stays in the middle and the stars fly right through. But in the video, it seemed the other way around. Like the stars were more equally distributed in the center, and the gas was more in stream. So I guess my question is, well, what am I misunderstanding?
Yes. So I think you're asking about the bullet cluster. So yeah.
Gas and stars.
So I would say I think it's a bit different. So the bullet cluster is it's a merger not of two galaxies, but a merger of two galaxy clusters. So they are like basically very large groupings of galaxies. And the bullet cluster is cool because in the bullet cluster we see a clear separation of basically the galaxies and all the stuff we can see in the dark matter. And in this case, it's different because I'm not doing anything with dark matter basically. Just look at so what's happening here basically is that the gas and the stars, they are both very much affected by gravity. But then the stars are, well, first of all, they're more massive, so they kind of stick around a bit more because they're not as easily affected by gravity. And the other thing is that the gas is not just the gas. It acts more like a fluid, let's say. It acts more like, it sort of brushes against other bits of gas, which is not so much the case for stars, which are much further apart. So it's not so much, I would say it's quite different from like a dark matter, which the point for dark matter is that it doesn't interact in any other way than gravity. Whereas for the gas that we see here, that does interact with other bits of gas. Hope that answers your question. Okay, one last question.
I have a small one if please asking. Is it dependent on the type of merger that the galaxies are going through, or is it also a matter of time that you mentioned that the mergers were like super visible, that they only just went through a merger because we had the tails? So if we were to wait maybe a couple of years, thousands of years, so we would maybe see like less obscure things?
Yeah, so the question is, does the obscuration and the properties depend on which point of the merger they're in? And I'll just pull up a picture of this. So, yes, it does, actually. In fact, it's also the same with quasars, actually. We think, so because quasars are, they are supermassive black holes that are growing, that are actively like, eating the material around them. Some astronomers argue that it's better to call them like quasar events rather than quasars because they just happen for some period of time and then they might not do so in the future. And it's the same for mergers because they're very dynamic processes. There's a lot happening, and that means that the point in time that you capture your merger matters for maybe whether there is a black hole that's actively growing at that point. And we also think that this feedback mechanism where a central supermassive black hole can actually blow out a lot of gas, we think that that is also a way that if these things are very dusty, they can also clear out the dust. So maybe in a couple thousand years, we will be able to see a quasar in R220 simply because the dust will have been cleared out by these winds coming from some quasar or coming from the stars. So yeah, that does very much matter, and that's one tricky thing about astronomy. We only see snapshots of the universe. We can't really take a galaxy and trace an individual galaxy back through time. We try to do that with simulations, but of course it's not something that we can do with our real data.